This is lesson 3.4, difference of two squares. So in the previous lesson you learned how to factor out greatest common factors. In this lesson your objectives are to factor out polynomials completely by applying the polynomial identities. You're going to be learning about these. And also that you can factor out a quadratic that is a difference of two squares. So the technical definition of a perfect square is a number that has a rational number as its square root. What are some examples of perfect squares? Well, square root of 36 is a perfect square because the square root of this number is rational. It's 6. If it was irrational, you get a decimal. Do you know all the rest of the perfect squares? Think of your times table. All the numbers that fall diagonal on your multiplication tables, 1 times 1 is 1, 2 times 2 is 4, those numbers 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144, and the list keeps on going, are all perfect squares. I'd strongly recommend that you memorize your perfect squares up to 100. This is going to prove very important for this lesson. To help you understand the difference of squares, let's try multiplying two binomials that will result in perfect squares. If you notice here we have x plus 3 times x minus 3. Now you have many different ways of solving this. You could have used the stack up method, you could use the FOIL method, or you can use the box method. Regardless, your answer when you multiply whatever method you use will be x squared minus 9. There's only two terms in this answer. If no matter which method you used, you found out that your two middle terms that you combined together was a plus 3 and a minus 3, plus 3x and a minus 3x that canceled out, and that's why there's no middle term. So what do we notice about both of these terms? Well, we notice that the numbers that we're adding or subtracting are the same, and our variables are also the exact same, x and x. So the variables and constants, minus their signs, are the same. So this is an example of a difference of two squares. The only thing that's different is the signs of the constants. One's positive and one's negative. So if we were to go backwards, if they gave us x squared minus 9, we should get, as our factored pairs, is x plus 3 and x minus 3. So how do we notice what's similar about this? Well, we have x squared. What is x squared? X squared is x times x. And what's the square root of 9? 3 times 3. These are both perfect squares. So if we bring one x here and one x there, and 1 3 here and 1 3 here, that's where these all come from. So we have a rule that when we use working with the difference of two squares, for all real numbers a and b, so a and b are going to represent either numbers or variables, if a and b are squared and you subtract them, their factors will always be the multiplication of each variable with opposite signs. I guess the best way to explain it. So a plus b times a minus b. And they gave you an example, x squared minus 16. X squared is a perfect square, and so is 16. So its result is the square root of x squared and the square root of 16. So the square root of x squared is x, the square root of 16 is 4, and when you write them out in factored pairs, the only thing that's different is you need to put a plus and a minus sign. So note, polynomials in the form of a squared plus b squared, or addition of squares cannot be factored in the same way as polynomials as difference of squares in the form of a squared minus b squared. So when you're finding the difference of two squares, notice that these are always going to be just two-term expressions or binomials where each term is a perfect square. So I have some questions for you. Underline the correct word or words to complete the sentence. The expression is a binomial. It contains two terms. The expression is a difference. It's a subtraction. Both terms are perfect squares. I can use the difference of two squares rule to factor this. So you would simply make two sets of parentheses. You take the square root of the first term, which is v, and write them in. And the square root of the second term, so square root of 10 is 10. So 10 and 10, and then you just fill in a plus and a minus sign. So there, you factored it. Before you use the differences of two squares rule, you must ask yourself, are there two terms? If there are, then you go on to the next step. If they're not, then you can't use this method. Are both the coefficients perfect squares? Are the variables and expressions raised to an even power? That's how you know if the variables are perfect squares. The variables have to be to an even power. All even powers will be perfect squares. And finally, does the term have a positive coefficient and the other one have a negative coefficient? So let's try this. Let's check each one of these questions. Look at this binomial. Is it a binomial? Two terms? Yes, of course it says it. X squared minus 4. Are both terms perfect squares? So the first term is a variable. Is that to an even power? Yes, it is. Therefore, it is a perfect square. Is the second term a perfect square? 4 is, right? The square root of 4 is 2. So we can fill it in. Our variables square root of the x squared is x. By the way, if you ever take the square root of any number that's to the powers, this is square root of 2, will cancel out. So a square root cancels out the any number squared. There we go. Sorry, couldn't spit that out there. The square root of 4 is 2, so 2 and 2, and you have a plus or minus. So there we factored it out. You can check by foiling or stacking to make sure you have the correct answer. So I'm going to show this with foiling. You may prefer box method, which I usually do too. But just for space reasons, I'm going to go on and foil this. X times x is x squared. X times negative 2 is negative 2x. 2 times x is positive 2x. And our last two terms, 2 times 2 is 4. We combine our two middle terms, which both of them cancel out, so you get x squared plus 4. So the problem checks. That's how you can always tell if you factored out a problem correctly. You should be able to multiply it out and you should get the original answer. Alright, let's try another one. Can we use the difference of squares rule with this problem? Is it a binomial? Yes, there's only two terms. Are both terms perfect squares? Now in this example right here, we have a coefficient and a variable on our first term. You need to make sure that both are perfect squares. So, whoops. So is 4 a perfect square? It's 2, right? So the square root of 4 is 2, so you write in 2 and 2. And is our variable to an even power? It is. So the square root of x squared is x, because x times x equals x squared. And then the square root of 16, which is 4. 4 and 4. And we have our plus and minus signs in between. Plus, minus, I know they're already written in there, but I just want to re-emphasize them. So that is this problem factored out. Focus question 3, we have 9x squared minus 81. It is a binomial. 9 is a perfect square. Our variable is to an even power, and 81 is also a perfect square. Square root of 9 is 3, so you fill in your 3 and 3 for our first term in each of the two expressions that we should get. X squared, the square root is just x, and the square root of 81 is 9. 9 and 9, and you have a plus and minus sign in between. Pretty simple, you just take the square root of both terms. It's now your turn. Please go on to the independent practice of 3.4 and complete those and turn them in. Ask if you need any help.